So next we're switching away from metric spaces and we talk about differentiation. So if we have a function on R, say, and then we say that that f is differentiable at x0 if the limit here, if the limit f of x minus f of x0, divided by x minus x0, if this limit here exists, as x go to x0. This quotient here is usually called the difference quotient. And it's always, of course, when you form this difference quotient, it's always assumed, obviously, that x is not equal to x0, so that the denominator makes sense, right? So if this limit here as x go to x0, if this exists, then we say that the function f is differentiable at x0, and the limit is called the derivative of f at x0, and this is how it's denoted. Okay? So now, the simplest possible example of this would be that suppose that you're looking at a function that is constant, so f is equal to f for some constant. C. Then if you're looking at this difference quotient, so f of x minus f of x0, x minus x0, well, the value at any point is c. So this here is c minus c divided by x minus y, x0. And so the denominator is 0, so this whole thing is 0. And so, of course, the limit, this is 0 for each x, and also each x0. So in particular, of course, the limit here exists. So the limit here of the difference quotient exists. And it's equal to 0, right? Because it's 0 for all x, for a given x0. So that would be like the simplest possible example. The second simplest example, second most simple example would be that you're looking at a linear function. So let's say that f of x is equal to x. Right? In this case, the difference quotient, so the difference quotient here well, this here is x, this here is x0. So this here is for each x and x0, this is 1. So the limit, of course, in this case also exists. The limit here exists, and it's equal to 1. Right, so in this case, f is differentiable. At all points, and the derivative at all points is equal to 0. In this case, f here is also differentiable. And the derivative at all points is equal to 1. Okay, so now in general, how do we compute the derivative of a function? how do we compute the derivative? And for that, there are some basic laws how to compute it. So there's these laws. The sum rule, what's usually called the Leibniz rule. The quotient rule. And then also the chain rule. Okay. Now let me look at the first three rules first. So I have two functions, f and g. They are defined, say, on R, but it could have been a subset of R. And I'm assuming that they are both, and both, right, actually we'll need one, okay, so both f and g are differentiable. At x0. Then we have the following, so we have the following lemma. One is we have that, so one, and this is really the sum rule. We have that the sum here, f plus g, so the sum of these two functions, this is the function that is just in x, it's just the sum of f of x and g of x. We have that this function here, f plus g, is differentiable at x0, and the derivative f plus g, the derivative of this at x0 is just the sum of the derivative. Okay. Let me prove this one here right away. So let's prove this. So we have the sum. So we are going to look at, so we form the difference, so form the difference quotient. So f plus g at x minus f plus g at x0, x minus x0. Right, so now what is this? So this here is, this is just f of x plus g of x minus, and then f of x0 plus g of x0. And then divided by x minus x0. Right? And so then you can split this up into two. You can write this difference quotient as if you split it up, if you collect the f's in the denominator. So I just collect the f's. And then afterwards I collect and I put it on two different fractions, separate them out, and then I collect the g's. And now you see that because f was differentiable at x0, this thing here, as x go to x0, this here goes to f prime. So this here goes to f prime of x0. This is what this difference quotient here. And this difference quotient goes to g prime of 0. So you have that indeed it does converge, and this is what it converges to. Right? And so this proves that the sum of these two functions is also differentiable, and their derivative is the sum of the derivative. Okay. The next thing we will prove is Leibniz rule, but before that, I need to kind of step back, and I want to, so before proving, so the next, maybe I'll just state it, and then we'll go back, and we need something. The next is what's called Leibniz rule. So it's all, you could also call it a product rule, but it's really quite generally called the Leibniz rule. And so this is when you're looking at the products of these functions. So the product function is a function in x that is just the product of f of x and g of x. And Leibniz rule, it says the following. That if f and g are differentiable at x0, then the product of these two functions here is also differentiable at x0, and the derivative of the product is the derivative of the first function at x0 times the value of the second function at x0 plus the symmetric thing in f and g, which is the value of f at x0 times the derivative of g at x0. Right, so the product is differentiable at x0 also, and this is what the derivative is. And in the notes, I just copied a little bit of thing, just for fun, from Wikipedia about Leibniz. That was kind of an interesting figure and played an important role a long time ago. Okay, so before I want to prove this, let me step back and let me make an observation about what it means to be differentiable at a point. So this is the next lemma. So you have a function f on R into R, and you assume that f, so if f here is differentiable, at x0, then I claim that then f here is also continuous at x0. Right? Okay. So in other words, being differentiable is stronger than being continuous. In a minute, we will see an example of something that's continuous but not differentiable. And so, okay, so now let's try to prove that. So, right, so I'm assuming that it's differentiable. So this means that this difference quotient here, this here has a limit, and that limit is the derivative, right, as x go to x0. So this means that, that there exists delta greater than 0, such that if x here minus x0 is less than delta, right? Of course, I'm assuming that it's not equal to x0. If it is less than the difference between x and x0 is less than delta, then this difference quotient here, then f of x minus f of x0, x minus x0, minus f prime of x0, this thing here have to be less than 1, right? I mean, this is just using that this limit exists, and I'm sort of using, in place of epsilon, I'm using 1, right? Okay. Now, so this means just multiplying over. And multiplying over, you get that f of x minus f of x0 minus f prime of x0. This thing here times, and I'm multiplying both sides, so I'm multiplying both sides by x minus x0. This is a positive thing, right? So I'm multiplying both things by that. So then I get this thing here, x minus x0, and then I get strictly less than x minus x0, right? Because this here is strictly positive, right? Because x is not equal to x0. So I have that, and so I get that. So I just split it up. So I have that f of x minus f of x0 is now less than x minus x0 plus f prime of x0 times x minus x0. And this is just the triangle inequality that we've used many times, just on R. Right. And so now you see that that if you now and this here, of course, I can also write like this. Sorry, I can just factor this out, and I can write it as 1 plus f prime of x0, no, like this. Fine. And so now if I want this thing here, so now you can, if you were to, right, so now you want to prove that f is continuous at x0, so you want this here to be less than some given epsilon, right? So given epsilon greater than 0, you let delta 1 be like the minimum of, if you set delta 1 to be the minimum of the delta that I already chose, so then I have this inequality, and then epsilon over 1 plus f prime of x0. Right. So if I make delta, if I choose delta like this, then I have this inequality. I fill in that, so now I'm assuming that this thing here is less than delta 1. So again, I have this inequality because it's less than delta. So then when I fill in here delta 1 for this, then I see that this thing here times this is less than epsilon. Right? This here holds when x minus x0 is less than delta 1. Right? Again, because if it's less than delta 1, it's less than delta. So I have this inequality. And then I can use that delta 1, since it is less than this. And then I get this inequality. Okay, so this proof, right, so this is really what we want to prove, right? We want to prove that if it's differentiable, then it's also continuous, and the continuity, here I proved it, with the, epsilon or delta, that you really should prove it like, okay? Now let's look at some examples. So this means that if a function is differentiable, then it's continuous. Let me give you an example of a function that is, so let me give you three examples. The first example is maybe the simplest one. So this is the function f of x that is equal to the absolute value of x. So f here is defined on r into r. And it's just the absolute value. And so the absolute value here, so we've seen before, so f here is continuous. It's continuous at all points, right? In particular, of course, at 0, right? But if you now form the difference quotient, right? Suppose that x here is bigger than 0. And now look at the difference quotient. So the difference quotient at x0 equal to 0, if you're looking at that difference quotient, and you first look at where x is positive. If x is positive, then f of x minus f of 0, x minus 0. This difference quotient here, if x is positive, then this thing here is just x. So this is x minus 0, x minus 0. So this here is 1, right? This difference quotient is 1. This is when x is positive. When x is negative, then f of x, if x is negative, then the absolute value is minus x, right? So the difference quotient here, f of x minus f of 0, which is 0, x minus 0. This here is just minus x divided by x, but this thing here is minus 1. So for all, if you're looking at the difference quotient, and that comes from looking at the derivative as 0, then when you approach 0 from the right, then the difference quotient is 1. When you approach it from the and when you approach it from the left, then the difference quotient is minus 1. So it doesn't have a limit, right? It has a limit from the right, from the left, but it doesn't have a limit if you don't restrict where it's coming from. So this function here is not differentiable. Yeah.
So you define what it means for like a minimum function as x approaches.
So okay, so this is right. So we did this earlier in the class. So if you take that the difference quotient here that this thing here is converging to some number, say a, right? This here means that for all epsilon greater than 0, there exists a delta greater than 0, such that if x minus x0 is less than delta, and again, x is assumed to be different from x0. If you have that, then this difference quotient here minus this a is supposed to be less than epsilon. And so that's this. Okay, and so you see again in this example that we just looked at, where in the example that we just looked at, where, so in the example where f of x was equal to the absolute value of fx, if you were graphing it, then this looks like this, right? And we saw that the difference quotient, when you approach it over here, the difference quotient was 1. When you approach it over here, the difference quotient is -1. So if you take any little interval around 0, then the difference quotient could be either -1 or 1, right? But even however small you make this little interval, it's not like that it converges to some number, because it is both, there are both cases where it's 1 and cases where it's -1. Okay, so that's like the first example. And again, of a function that is continuous, but it's not differentiable at 0. In this case, it was a 0. Maybe a little bit more interesting example along the same line is the following. So so this is again a function on R into R. And I said f of x equal to x times sine of 1 over x. This here is not really defined at 0, so I need to define it also at 0. So when x is equal to 0, then I just set it equal to 0, and otherwise I set it equal to x times sine of 1 over x. Okay. And so the thing is that this function here, so f here is continuous. In particular, it's continuous at 0. It's continuous. It's actually continuous everywhere, but it's mostly interested in it at 0. The graph of this. So remember that sine function looks like this. That at 0, at pi, at 2 pi, at 3 pi, and so on, at all of these, right, at all integer multiples, also for the negative ones, at all integer multiple of pi, sine function vanishes. And in between here, it is at pi over 2, it achieves its maximum, which is 1. And so the function looks like this. So this here is 1. Right, that's how a sine function looks like. And so now if you're looking at sine of 1 over x, that's going to be a function as you're going down. So if you're looking at this here was sine of x. But if you're looking at sine of 1 over x, as x go to 0, this here becomes very large. So this means that as you're going to 0, it goes very rapidly through these periods where it oscillates between -1 and 1. So the value here is -1. And so it will look like this, that it will again, if you're looking at, it will again fluctuate, but it will fluctuate much more rapidly. So if this here, say, was 1 over pi, at 1 over pi, 1 over pi is the same as pi. There it would be 0, and it would like fluctuate. It would fluctuate, so it would look like something like this, but it would fluctuate. You know, and then as you're going away, it will fluctuate less often. Right? So as you're going down towards 0, it will fluctuate a lot. Right? It always, because sine always is between -1 and 1, the value here will always be between -1 and 1. But as you're going towards 0 from the right or from the left, it's going to fluctuate more and more. Right? As you're going away from 0, it's fluctuating less and less. Okay, so this is the function I'm interested in, and so, but when you multiply through by x, then you see when you multiply through by x, it's fluctuating, but it's always fluctuating between -1 and 1. If you multiply it by x, then as you're going to 0, this here will squeeze down, and it will become, the fluctuation will be 0, at 0. So it's easy to see that this function here is indeed continuous. Right? But let's look at the difference quotient. So the difference quotient. So if we're looking at the difference quotient, so we're looking at, and we just look at the difference quotient at 0. So this here is the difference quotient. And so it's x sine 1 over x. The value at 0 by definition was 0. And so you see that now this here, the x, this here becomes just x sine 1 over x divided by x. And so you see that this here cancels with that. So you just get sine 1 over x. And so you see that now as x goes to, so when x here goes to 0, this here fluctuates, this here fluctuates between -1 and 1. But it doesn't have a limit, right? Because it's fluctuating wider and wider, right? So this is an example again. This is another example of a function that is continuous at 0, but not differentiable at 0. It's actually much worse than the previous. The previous one, the previous example that was this example is much more tame. It is not differentiable at 0. But if you were strict to just positive things, then it would be differentiable, right? If you could also define derivative. So in general, when we define derivative, we let it be defined in a neighborhood of that point, so on either side. But if you were considering where you were allowing the function just to be defined at this point, and then to the right, say, or to the left, then this function would be differentiable, right? But in this example here, it doesn't matter if you restrict the interval to just to the right or to the left, it's still not differentiable. Okay. Right, and so this example is something about that it fluctuates wildly, and that is causing it not to be differentiable. If it wasn't, again, if you defined it, if you didn't have this kind of, the x here is sort of serving as some sort of, it's dampening how much it's fluctuating, right? So if there wasn't an x here, then this function would just fluctuate, and it wouldn't even be continuous at x0, right? But once I put this x on, then it becomes continuous. If I put another x, So if I'm looking at f of x equal to x squared times sine 1 over x. Suppose I'm looking at this function. So now I have sort of dampened the fluctuation even more. And so if I again looking at the difference quotient, so I'm looking at this function, maybe I should be more careful. So again, at 0, I need to define it separately. So I define a function that is 0 at x equal to 0, and then it is x squared times sine 1 over x. Otherwise, if I'm looking at this function, then I claim that this function is in fact differentiable at x at 0. And so let's look at that. So again, I'm looking at the difference quotient. And the value at 0 is 0. So I have this. And so this here is now just x squared sine 1 over x. This thing here is then x. And so you see that this difference quotient is just this. But this here does convert to 0 as x goes to 0. Right? So this function is actually differentiable. Right? It fluctuates, but it's more mild the way it fluctuates. Okay. Now let me get back to the rules. So we proved one rule, that was this sum rule. Then the second rule we're interested in is when we're looking at the Leibniz rule. So we're looking at the product of these two functions. And each function is assumed to be differentiable at x0. And then we claim that the product function is also differentiable at x0. And this is the formula for the derivative. Right? To prove this one here, I need this fact that we have now proved, that if it is differentiable, then it's also continuous at that point. Okay, so I'm going to use that fact. And so, and now, let's prove of Leibniz rule. So we have these two functions. We're looking at f of x. We form the difference quotient. So this is the difference quotient, x minus x0. We do this trick that we've done a bunch of times before when we also looked at products. If we had two sequences and we looked at the sequence that was the product of these two, right? So if you have, just a reminder, that, I mean, it's not like, but